Hello and welcome to the iolite 3D Trace Elements DRS webinar. My name is Ben Paul and I'm the iolite product manager, and with me today is Joe Petrus, iolite's lead developer. So today we'll be talking about the 3D Trace Elements DRS, our new Trace Elements package for iolite. To give you an overview of what we'll be discussing today, to start off, we'll talk about some theory of how we calculate concentrations from mass spectrometry data in laser ablation. And I'll be talking a little bit about the ideal setup that you might want to use with this DRS. I'll also be talking about how we construct our 3D calibration curves, or actually surfaces. And then we'll look at different ways to normalize our data, taking into account yield and those sorts of things, looking at internal standards and some normalization. We'll also be introducing this idea of affinities and using those to perform downhole fractionation correction for elements that need it. And finally, we'll be introducing this experimental feature, this sort of new feature that we've added, that is this residuals correction. There is an example data files that you can download to go with this. After the first part, the theory part, which is not interactive, then we'll actually work through some example data sets, and you can follow along with those if you download this data set, and there's the link for the data set. So why did we create this DRS? And we've been thinking about this for quite some time, a number of years. I may have spoken to some of you about it in the past, but the real reason why we wanted to do this was because we wanted to allow iolite users to be able to use more than one reference material. We also wanted to incorporate a bunch of features that have been available in iolite in the past, such as some normalization, but we haven't really advertised or explained how they are used. And we wanted to bring that together with this new 3D trace element approach that we've developed. And we also wanted to add some advanced features such as downhole fractionation correction. We are writing up this approach as a paper. We're hoping to submit it before the end of the year, and that paper is basically a written version of what we will be going over in this webinar today. So let's look at some theory. How do we go from the counts per second that our mass spectrometer records through to concentrations, which is what we're actually after? One way to do it, and I would say kind of the more conventional way to do it, was to construct a calibration curve. And we do that by plotting along the x-axis the concentration, and on the y-axis we plot the intensity. So if we have a reference material which has a known concentration, so we can plot it as one value on this x-axis, and we can plot our results for the reference material, the intensities that we get here. And that will have some spread in the y-axis, but not in the x-axis, because we know the concentration, it only has one value. And if we were to repeat that for a second reference material, so it also has just a single x value, and plot our different results that we get throughout the experiment, we'd also get some spread in the y. And if we fit a line to this using something like ordinary least squares fitting, or maybe a weighted least squares fitting, we get this dashed line here, which is a calibration curve. And we can use that to calculate the concentration in our unknowns based on their intensity. So let's look at the maths behind this. And before I do, I'd just like to introduce some of the symbols that I'll be using in our equations. So wherever you see a lowercase c, that's referring to the concentration. Where you see an uppercase R, that's talking about count rates. And in particular, whenever I say counts per second or count rates, I'm talking about the baseline subtracted count rates. We're not using the raw counts at all in any of these calculations. Where it has the subscript samp, that means that it's talking about the sample. So for example, C subscript samp means the concentration in the sample. And similarly, subscript RM means that it's talking about the reference material. So R subscript RM would be talking about the baseline subtracted count rates in the reference material. And you'll see this I, that's just referring to a particular element from our suite of measured elements. It's just one of our elements that we've measured. So with those definitions sorted, let's have a look at our first equation. So we can calculate the concentration in our sample, C subscript samp, for element I by looking at the count rate, the baseline subtracted count rates in our sample, R samp, subtracting off the intercept of the calibration curve and dividing by the gradient of the calibration curve. One way to think of this visually is that we take the intensity that we measure for our sample and we go across to our calibration curve, and then we can read off from that our concentration. But what about when we've just got a single reference material, like we quite often use in geosciences and has been the case for most of iolite applications in the past? How do we construct a calibration curve with just a single reference material? Well, we start by assuming that we have a zero intercept. So now we have 2 points, one up here and one down here. If we have 0 for the intercept, and the intercept is this BI factor here, we can ignore that, and so our equation becomes this. It's just the count rate divided by the gradient. And if you remember from high school maths, the gradient is just the change in y over the change in x. So in this case, the change in y is just the intensity of our reference material, and the change in x is the concentration of our reference material. And so we can actually change this around. We can substitute M, we can substitute C, the concentration of the reference material, and the count rate of the reference material. They're actually flipped up, so the gradient was actually R on C, but we're flipping it over because we're dividing by M here. So in iolite though, we want to keep our time resolution. So how do we do that? Well, what we do is instead of using the average count rate or using all of those count rates, we actually use the spline of the count rates for our reference materials. So in this equation here, instead of using some average value, we actually use this spline. And how do we do that for every single data point? Well, we interpolate this spline onto the same sampling frequency, that is the time resolution for our normal channels. And so we have a value for our reference material at any point in our experiment. This allows us to calculate a concentration for every point in our experiment. The great thing about this is that it provides time resolution. In those previous images, those previous graphs that we're looking at, we're using all of our reference materials to calculate a gradient, and then that takes away the time resolution. By doing it this way, we have time resolution, but it does rely solely on a single reference material. And that can be a problem if there are uncertainties in your reference materials, or if your reference materials are very noisy. And also, it means that you have to choose a reference material that has some value in it for all the elements of interest, and that matches roughly with your sample. And that can be quite tricky to do. So this approach here, where we're using this count rates multiplied by the concentration of the element in the reference material divided by the count rates in the reference material, is called the semi-quantitative approach. It's called that more for historical reasons. It is actually fully quantitative. You do get a number from it. It doesn't just tell us high or low. But it doesn't have any accounting for yield, changes in yield between our sample and our reference material. So what do I mean by yield? Well, we know that there are small differences in the ablation characteristics of different materials. That is, those matrix effects that you'll hear about. Those differences result in different amounts of material entering the plasma. And then if there's different amounts of material entering the plasma, that means there'll be different amounts reaching the detector, so we'll get different count rates. It also changes the properties of the plasma and a bunch of other things which I've just put in as etc., etc. So we need some way to account for these differences in the ablation characteristics between our sample and our reference materials. And we do that by calculating the yield. The yield here is represented by Y of element I. So our yield is really just the count rates that we get for a given concentration. And this has units of counts per second per microgram per gram, or you could say counts per second per ppm. If you have high yield for a given concentration, it means that you have a higher count rate. And if you have low yield, you'd have a lower count rate for a given concentration. We can only calculate this for elements where we know the concentration. So that's why I've included the RM here, but you can also have elements of known concentration in your sample, as we'll see in the next slide. This Y value is referred to as the K factor in Liu et al., it's a popular publication about some normalization, and we'll come back to that later on. So this is our yield factor. The great thing about the yield calibration is it takes into account those differences in matrix effects by using an element of known concentration. If we use a single element of known concentration, we call this our internal standard. Internal standards tend to be something that's easy to measure, something with high-ish concentration but interference-free, and they're unchanging in the sample and the reference material. They can be determined from stoichiometry for some minerals, or they can be measured by a different technique. That brings us to the Longrange et al. Equation. Before we show the equation, I just thought I'd remind you of this semi-quantitative equation because it's a really fundamental equation and we'll keep seeing it over and over in the theory side of things. So remember, it's just the count rate in the sample multiplied by the concentration divided by the count rate of the reference material. And also this yield factor again. I just thought I'd show that again. So what was Longrange et al.'s equation? Well, they said that the concentration of element I in the sample is equal to the count rate of element I in the sample divided by this factor S. And S is this count rate in the reference material divided by the concentration in the reference material multiplied by this factor in brackets here. The first thing you might notice is this looks quite familiar. If we have this R divided by this part here, that's exactly this part here. That's exactly the semi-quantitative approach. Then what is this part here in the brackets? Well, if we look at it, it's the count rate of the internal standard in the reference material divided by the concentration of the internal standard in the reference material divided by the count rate of the internal standard in the sample divided by the concentration of the internal standard in the sample. And you might notice that this looks exactly like this. And that is because this is just the yield factor of the internal standard in the reference material. And this bottom part is just the yield factor of the internal standard in the sample. So we're looking at an element of known concentration in both our standard and our sample. And this gives us a yield normalization factor. And it's unitless because this will have units of counts per second per ppm, and so will this. And really, it's just a factor that we apply to this equation so that we can take into account yield differences. This brings us to some normalization. The idea behind this, and it was originally the first paper that described this, I think, came out in about 2000, but the most popular one is this Liu et al. Paper from 2008. And the idea behind this is that the sum of all element concentrations in our sample should be equal to 100 weight%. It just makes sense that if you add up all the concentrations, then they should come to 100%. We can express this as the sum of all concentrations being 100 weight%. And with that, with knowing that, we can then express the concentration of any element as the concentration of element I in our sample is equal to this value here divided by the sum of all these values here. And remember, this rate, concentration and rate is our semi-quantitative equation. So we're saying that for any element, it can be expressed as a proportion of the sum of all the semi-quantitative concentrations of all the elements in our sample. And we just multiply it by 100 so that we go from a fraction to a weight percent. The great thing about this is it doesn't require an internal standard. We don't need to know the concentration of any particular element to use as an internal standard. We don't have to have an element that's unchanging in our samples. Rather, we're using this property here that all the elements summed together should come to 100 weight percent as the yield normalization factor. We can use different numbers other than 100% if we know that there are some elements that we haven't measured that are in our sample. So for example, if there were 3 weight percent volatiles, and we know that we can't measure oxygen or hydrogen, then we could say that we know our sum should come to 97% instead of 100%. As I mentioned, it doesn't require an element that is known unchanging, that is an internal standard, but it still takes into consideration this yield normalization. However, it does require all elements that we can't assume something about, that can't assume their concentration. All of those need to be measured. And especially in the geosciences, this means that you could be measuring tens of elements. In the example data set that we've got today, there's about 50 elements, and that's because you need to measure all those, or measure every element that you can't assume some value for. This has implications for your sweep time. So if you're measuring 50 elements, all with 10 milliseconds dwell time, then that means you're going to have a very long sweep time, which will affect how fast, or your time resolution, which will then affect how fast you can scan. And it also requires some knowledge or some assumptions about your oxidation states and your volatile contents. And if you're measuring a sample that has different phases, such as different minerals or different tissue types or different alloys within the sample, then you do need to either need to know about those different phases, or you need to make some assumptions. And as we'll see later, we do need to know about the oxidation states. One of the last things that I'll talk about is this downhole fractionation correction. So those of you who have done uranium lead in the past will be quite familiar with this concept, but the idea is that, and this only applies to spot analyses, when the laser switches on, we have this increase in signal, which we can see here. We've got calcium and strontium. And as we drill down into our pit, because less material is escaping, we have a decreasing signal until we turn the laser off and we go back to baselines. Now, sometimes there can be a different amount of signal change between our element of interest and our internal standard. But in some of those previous equations that I've shown, we've assumed that the ratio between the two doesn't change. That's not always the case. And it depends on the matrix, and it depends on which particular element you're talking about. Whether or not you'll see this effect and need to correct for it will depend on your system and how noisy it is, and it'll also obviously depend on what sort of samples you're measuring and things like your spot size and your pit dimensions. So with that theory out of the way, let's talk about our new 3D Trace Elements DRS. It provides time-resolved multi-reference material calibration. So in that first graph that I showed, the calibration curve, that's not time-resolved because we're taking all of our results from our experiment to calculate that curve. And we're just using the one curve for the entire experiment. However, in this approach, you still get time resolution and you can still use multiple reference materials. We also offer a range of fit options to fit those points to create our calibration curve. And we can still use our internal standards or some normalization to take into account the differences in yield between our reference materials and our samples. And we can do it using criteria, which is a bonus that I'll come back to later on. It also can do downhole fractionation corrections, which, as I'll show later, can greatly improve your precision. The example that I'll show is an improvement of about 30% more precise. And it also has this process where it can calculate a yield normalization factor between your reference materials. So if you're measuring sodic glass materials such as your NIST 612s and 610s and your basaltic glasses, they're going to have slightly different yields because of their different matrices. But we can calculate a value to normalize them all to one reference material. So we get rid of these differences in our yield when constructing our calibration curve. And we put it all together into one handy package. So we have some example data sets that you can download to follow along with this presentation. In the first data set, there is this Gabbros map.io4, which is a mapping experiment. This is just where we're rastering across the sample and we're not drilling any pits. And in that, we're measuring NIST 612, NIST 610, NIST 612, BCR2G, BHVO2G, BIRG, and some Gabbros, some Gabbro scan lines. We won't actually be using the Gabbro scan lines in this example because we're trying to demonstrate the improvements in accuracy, and we can't do that with unknowns. We need to look at something where we know what the values should be, and for that we're going to be using BIR1G as our check. In the Gabbros spots experiment, this is a spot analysis experiment where we've measured NIST 612, BCR2G, BHVO2G, and some Gabbro minerals. Again, because we're looking at the process, we're not going to worry about the unknowns. We're just going to be looking at our reference materials and seeing what effect our workflow has on those. And I just wanted to point out that even though we're using geomaterials in these examples data sets, the corrections and the concepts that I'm talking about may well apply even more to non-geoscience experiments where you don't have such well-characterized and well-behaved glass standards. So we chose these because we could test things very well, very easily, but that's not necessarily to say that this is the best application of it. Just before we jump into iolite, I thought that I would show what we consider to be the ideal experiment setup for this DRS. And you can see the way that we've set up our experiment is that we have a series of calibration blocks. We have one here, and one here. And in each of these blocks, we have several measurements of our different calibrants. And I'm just using the word calibrant here to mean a reference material that's used in the calibration compared to secondary reference materials, which are also reference materials, but they're not used in the calibration. So we have several measurements of each of our calibrants here, and then a gap of about 30 to 60 measurements, and then we do the same thing again, and then we keep doing that throughout our experiment, making sure that we have a final block at the end of our experiment. In between these blocks, we have our samples being measured, and interspersed with those samples, we have some secondary reference materials. And it's important that these are not included in the blocks, but are rather in amongst our samples so that we can treat them exactly like our unknowns. When you're working with splines, splines tend to be most accurate around the tie points, which are going to be these blocks. And they can do weird things in between the tie points, and we want to keep an eye on that by having standards measured in between our blocks. So it makes sense to intersperse them with our samples rather than including them in our blocks. The time gap up here that we recommend is between 30 and 60 minutes, but really it will depend on a few factors. The most important one is how much sensitivity drift you're getting. If you get a lot of sensitivity drift, you'll want to decrease this duration, but if you have a very stable system with very stable elements and very stable response, then you can extend this interval. And of course, it'll come down to how much of your reference materials you want to use up. In the examples that we use here, we've collected quite a few scan lines across our reference materials, and it's a little bit of overkill, I guess you could say, but it was to sort of prove the concepts. So let's look at our Gabros map file. In this, we've already done the data import and created all the selections for you, and we're going to be using NIS 610 and 612, BCR2G and BHVO2G as the calibrants. As I said, we probably don't need that many, but we're doing it for this example. And we're going to use BIR1G, which was measured in amongst the samples, as our secondary standard. So let's have a look at that in iolite now. So when you open the file, the experiment, you'll see that there is a single mass spec file and a single log file. And when you look at the samples, you'll be able to see, if we sort by start time, that we've got 3 NIS 610 runs, 3 BCR2G runs, 3 NIS 612 runs, 3 BHVO2G runs, and then we start measuring our samples. And in between our sample measurements, kind of randomly dispersed in there, are our BIR1G measurements, before we come back to measuring our blocks again with NIS 610, BCR, NIS 612, BHVO. So those are our blocks, and with our samples between them. And if you have a look at the time series window, you'll be able to see that we have our blocks like this, our blocks, and our secondary reference materials interspersed with our samples. So let's look at the 3D Trace Elements DRS. If we click on this here, it'll show you the settings window. There are 4 main parts of this window. There is the external standards and channels part up here, and you can see all of the channels that we've measured. In this case, we have quite a few. Some of them we could definitely have dropped, but we just put it in for completeness. And you can see we can set reference materials and a few other settings over here. On the right-hand side, we have all of our selections, and they're grouped according to the selection group that they belong to. And we have some settings for setting internal standards. This is the selection side of things on the right-hand side. Down here we have our visualization part, and we can't see anything in that yet because we haven't set any settings, but we'll come back to that in just a sec. And down the bottom we have some miscellaneous settings like masking and index channel and this affinity correction. So the first thing we want to do is actually set some calibrants, set which reference materials we want to use as calibrants. Now in this list you can actually set values for each individual channel, but if we want to set for all channels, we can just click on a channel and hit Ctrl+A, and that will select all of our channels so that we can set properties for all the channels at once. And if we use this drop-down menu here, it will allow us to select which reference materials we want to use as calibrants. In this case, we're using BCR2G, BHVO2G, NIS 610, and NIS 612. And when you do this, depending on the speed and processing power of your computer, it might take a little bit to actually run some calculations. And we'll talk about what those calculations are now. So you can see that now in each channel it shows which reference materials we're using to calibrate for, and you can see that we now have something in our visualization panel. We can actually pop this panel out and make it bigger so that we can see what's going on in there, but we can't close this panel, because if we close this then we'll lose all the information in it. What we do instead is we click this button again to pop it back in again. And you can see the first thing that comes up in here is the 3D tab gets some data and this surface plotted in it. And we can see these blocks have been plotted along time axis, and we now have some data points in there. I should explain the axes of these. If we look at it in just the sort of right sort of orientation, we can see that the x-axis is concentration and the y-axis is intensity, just like in our conventional calibration curve diagram. But we've added this third dimension, the z-axis is now the time, so that we actually, instead of having a single curve, we have a calibration surface. We'll talk a little bit more about that in just a sec. How did we get to that surface, and what were those calculations that it was doing that was slowing us down when we were selecting our reference materials? Well, the first thing that it was doing was breaking our data up into blocks. And we can see our blocks when we click on this Blocks tab. When we click on that, we can see the data for our first block, and we can right-click on it and say, show me a legend. So it will show us what reference materials have been used to construct this block. We can move back and forth in our blocks using this, so we can see the 7 blocks of reference materials that we've measured. And on the top left corner here, we can see our slope with its uncertainty, and the intercept and its uncertainty, and an R-square value for this block. How did it work out where the blocks were? Well, we can look at that by clicking this wrench icon. And this will show us the block assignment window. We can open this up a little bit better, but what it shows is all the selections of the calibrants that we've chosen and how it's broken it up into blocks. They've been color-coded according to each block. The color here matches the color down here. And this is showing total beam versus time. And for each of our blocks, it's colored them in according to which block they are. The way that iolite by default will automatically try to determine these blocks is using this simple approach up here. The simple approach just looks at the gap between the selections. So within a block, the gap between selections will be very short, but between blocks, it will be quite a large gap. And so that's how it knows where the blocks are broken up. If that doesn't work for you, we've provided some other options as well. If you click here, you can see that we've got a clustering approach, which is just a k-means clustering approach, and we can tell it how many blocks to break our data up into, our selections into. So if I decrease this, you can see that it's actually joining blocks together because I haven't put in the correct number. The correct number is actually 7, and you can see that when I put that in, it's actually broken our data back up into blocks. We also have an auto clustering approach. If you do click this, it will take a little time to run because it's automatically running a lot of calculations to try and work out what the optimum number of clusters are. And it will work, but it just takes a little bit of time, and it will basically find 7 as well here. In this case, it works fine to use simple. If none of the automatic approaches are working for you, you can use this assigned option where you can just type in what values you want. And so you can actually go through each selection and tell it which block it should be assigned to. We don't have to do that in this case because we've set up our experiment using the ideal approach, and so we can just use this simple approach. So now we know how it's broken our calibrant measurements into blocks. So now we can look at those blocks, and as you can see as we move through, we're getting quite a bit of difference in the slope and the intercept. And we can see here how well each one has fit, but it's a little bit hard to see that for all of them at once. So we have this fits tab here, which will show you all of the fits for the different blocks at once. And we also have another way of visualizing that, which shows how the slope, which is in blue, and the intercept, which is in red, changes with time. So you can see our slope is increasing here, or this is our gradient, and our intercept is changing with time. This changes depending on which element is selected here, and if you have multiple elements chosen, it will just show the first one in the list. We're going to keep looking at lithium because it's a reasonably interesting example. And there's this fractionation tab here. We're going to come back to that at the end when we talk about downhole fractionation. So now if we go back to our blocks tab and just have a look at, say, the first block, how did we get this calibration curve? So this red line is our calibration curve. How did it calculate that? Well, we can choose which fit model we want here. And we can choose between these options. What these letters mean is shown here. So OLS stands for ordinary least squares, WLS stands for weighted least squares, ODR stands for orthogonal distance regression, and RLM stands for robust linear model. All of those, if you type into Wikipedia, you'll get an explanation of what they are. They're all very standard, but they do fit and treat the data slightly differently. Some of them will be more robust where you have outliers. For example, the robust linear model and the ODR might handle outliers better, or the ODR is really good for if there's some uncertainty or noise in your concentration calculation, so it handles that better. And the final one is the York approach, which is supposed to be a great one for handling outliers as well. That one is less common, but it comes from this paper here. And in this data set here, you can actually change which fit model you want to use using this selector here. And just like before, you can select many of them and change which model you're using. I've gone through and tested this, and there really isn't much difference between any of these first four, and if you select the York one, there'll be a very minor difference, and it depends on the measurements. So you need to choose based on your measurements and the nature of your data which one you want to use. So now let's look at, now that we've looked at how for each block it's calculated a calibration curve for each element, we can talk about how it uses those to create a 3D surface, 3D calibration surface. So if we look at this plot here, we can try to show the different blocks. And I've tried to plot them in by showing these grey lines. Now for each of our blocks, we have a calibration curve which has a gradient and an intercept. And then to create our surface, we just interpolate between those blocks the gradient and the intercept. And that's what we're doing here. You can see that between our different blocks, we're interpolating, and that will create our surface. This means that for any point in our experiment, at any time value, we have a gradient and an intercept that we can use to calculate our concentration. You can choose how those gradients and intercepts are interpolated by you changing the spline type. And you can see that that's done by this spline type button here. So if we look at this sort of end on so that we can see it a little bit better, we can go from a smooth spline through to some sort of step function. This is a linear step function where it's just a linear fit between blocks. We could go to a step linear function where it has the value of the gradient for each block until it reaches the next block. Or we could go all the way to a mean value. And when you choose mean, it's actually just taking the average gradient and average intercept for the entire experiment. And this is exactly like a traditional 2D calibration curve. So you can actually go back to that if you want to check your results that have been calculated using a traditional calibration curve. One thing that I haven't mentioned yet is the ability to force our fit through zero. And this can be really handy if your reference materials, if you don't have any reference materials that are near to zero. So you can see here our reference materials all have high-ish silica content. So we can actually use this button here to tell it to force through zero. In this case here, because I've got the York function, it's not doing a very good fit, but we can see that if we use ODR, it'll do a much better fit. So with all these settings that are available to us, it can be a little bit tricky to work out how we're improving or how much we're improving our accuracy. So let's just have a look at that. Before I do that, I'm going to select all of my elements and I'm just going to use the ODR fit, and we'll just leave it at that for a sec. I'm also just going to switch off internal standards, and at this point all we've done is calculate our calibration surfaces. Well, we've determined our blocks and we fit all of a calibration curve to all of our blocks, and we've used that to calculate a calibration surface. But in the and I'm just going to change that back to auto smooth. But we haven't actually calculated any final results. We haven't calculated our ppm channels, and we do that by clicking the Crunch Data button. Now, depending on how many channels you've measured and how many blocks and how much data you've collected, it will change how long this takes. In this case, we didn't actually see the import stage, but it was about 30 megabytes of data because it was measured over a reasonable amount of time. We did that because we wanted to get as much sensitivity drift as we could. And we are measuring a lot of different channels. As you may have seen, there was about 50 channels. That said, it will run this first approach in about 20 seconds or so. So now we have, if we were to go to our time series tab, you can see that it's calculated a bunch of baseline subtracted channels, and then using that, we have our slope and intercept channels, which will show how they've been interpolated with time. We can ignore those for the most part, and now we have ppm channels as well. So how do we tell how our accuracy is improving using all these different settings? If you go to the QA/QC tab, we can now run a check on those secondary reference materials that weren't included in the calibration. In this case, it is our BIR1G sample. And if we click on that, you can see that we have our plot as normal, and I'm going to assume that you're all reasonably familiar with the QA/QC modules, and in particular the secondary check. And just like normal, we have our table showing how far our average result for BIR1G is from the accepted value. So our average value for lead is 4, the accepted value is 3.7, so we're about 9% off in this case. Now, I did mention that we have a few elements in here that we could have omitted. The two worst offenders are the beryllium and the bismuth down here, and you can see this one's 33,000% off. It's a long way off at this point, and the way that we've calculated data so far. They actually won't get much better. They are basically very low in these samples and very poorly calibrated. The thing that I wanted to show though is down the bottom here, we now have this new factor called the sum of absolute percentage differences. And all it is if we were to take the absolute value here, so we're ignoring plus or minuses, and summed up all these values, this gives us one value for our accuracy. In this case, it's 48,000%. And that's because that's mainly because of a couple of these results being miles off. But it does give us one value that we can use to see how it affects see how our changes to the DRS affect our accuracy. So now we're going to go back to our DRS, and we're going to change one setting. We're going to force, for all of our channels, we're going to force the fit through 0. And so I've just clicked that button, and it will now apply that to all of our channels. You can see now it is checked for all of our channels, and we're just going to crunch the data again. And as I mentioned, this fit through 0 is really helpful where your reference materials are either very noisy or they're all clustered a long way away from 0. This just sometimes gives it a tie point somewhere down the bottom of the calibration curve. So again, it will run through and it will calculate the baseline subtracted channels and the blocks and the calibration surfaces, and then it'll store them for each channel. And now we have some results. So to get our updated results, we're just going to click this run button again, and you can see that forcing through 0 has made a big difference to our accuracy. And without going through each individual channel, we can just look at this summary value down the bottom here, where we've gone from tens of thousands down to about 1,300. So that forcing the fit through 0 was actually quite advantageous for us. And this is all just semi-quantitative. We haven't used any internal standards or subnormalization to account for differences in our yield. Now we can look at doing that. Before I do, I'll just check to make sure I've covered everything. That was one thing that I forgot to mention, was that this spline type here is what will determine our calibration interpolation through time. It doesn't take into account any of these spline types. So you can see this one here is doing lots of craziness, but that spline is not really used at all in this calibration. So we could ignore these for the time being in the time series window. And this is the one that you need to worry about. So how do we take into account this yield factor? Actually, before we do that, let's talk about yield normalization for our calibrants. Remember that we've got two different types of glasses for our calibrants. We've got basaltic glasses and we've got sodic glasses. The way we do that is we choose a main calibrant that everything else is referenced to. For the remaining calibrants, for the elements that are in common with our main calibrant, we calculate a yield factor using that y equals equation that we had before. We do that for each of the elements that are in common, and then using that we can work out a median yield. I've said mean here, but it should actually be the median yield so that we don't have any massive outliers, or we have less effect from massive outliers. Once we know the median yield between our main calibrant and each of our other calibrants, we can apply that yield calibration factor to each of the other calibrants. And this then will get rid of the different matrix effects for our other calibrants. And we do that up here. So this can be turned on or off, and you can choose which is your main calibrant here. In this case, we're going to use BCR2G, but really it's just making sure that yield differences don't affect our calibration surface. Now let's look at applying internal standards. And you can do this just like in the original Trace Elements DRS. We're doing it over here using this right-hand part of our DRS settings window. If we click the checkbox up the top here, it will then allow us to set values for our internal standards. And just like in Trace Elements _DRS, we can click on one selection and hit Control A, and it will select all of our selections, and then we can tell it which element we want to use. In this case, we're just going to use calcium 43, and when we click plus, it'll automatically get the values that we want and fill in the rest of the table for us. It won't do that for our unknowns, of course, because it doesn't know what the calcium value is in our unknowns. But for all our reference materials, it will take the value stored in our reference material files and fill out that table for us. So that's great. So now we can hit Crunch Data, and now we have in our trace element calculation, we now have some control over our yield values. And what we'll actually see in this case, in this particular data set, is that it doesn't have a really big effect on our accuracy at this point. We'll just wait for that to finish calculating. And now we'll go back to our QA/QC module once it's finished. And we can click Run again to see what effect it has. So we're at about 1300 total % different. And you can see just from the graph that it hasn't changed too much. And it's actually just gone down to about 1100. So in this case, yield normalization doesn't have a huge effect, but it really depends on your data set. That's using internal standards. And for a lot of data sets, that might be sufficient. But what if we want to use some normalization? So to use some normalization, we need to select which elements we want to use, and we need to set the sum value that we want to use. So we can do that here by selecting all of our selections again, and instead of selecting just a single value, single channel or element, to use as our internal standard, we're going to click Select All. Now this will take just a little bit because it will be applying those settings to each of our selections for each of our elements. So it'll just take a little bit to apply that. But once it's done that, then we can set our sum value that we want. And we can do that just by clicking this value button here. So if we want to sum up, if we want to use 100 weight% sum, we can set that here. And if we're assuming that our elements are all in the presence of oxygen, we can select this weight% oxide here to say that we haven't measured oxygen, but we know that oxygen is going to be a big part of our sample, so we can set that as weight% oxide and it'll take that into account. So now that we've done that, we can click Crunch Data, and that's all you need to do to use some normalization in this new DRS. And as we'll see once it finishes calculating again, that in this case again, it doesn't make a really big difference, but remember, we didn't have to have any knowledge of our of a particular internal standard element to be able to apply this correction. And so now, if we look at our updated results, so we were at about 1173. And after our correction, we're just down by a little bit. So in this case, we've gone from using an internal standard to using some normalization. And the reason why it doesn't have a very big difference is because we were already accounting for yield differences by using an internal standard beforehand, but we had to know the concentration in one of our elements. This is doing the exact same correction, but without knowing something about one of our elements. So that's how we do yield normalization. Sorry, sum normalization. But what about when we have our image data, where we may be going across different phases in our sample? In this example here, we have apatites, we have silicates, we have oxides, and we even have some sulfide blebs in this case. Now, each one of those is going to potentially have a different sum value that we want to sum it to, and whether or not it's in the form of oxides. That's because if we look at, say, apatite as an example, apatite can have up to about 4 weight% volatiles. I say volatiles here, but I mean like water and chlorine and fluorine. And that's based off just this website data here. So we can't measure those, so we know that our sum should be 96 weight% instead of 100 weight%. So how do we account for that? Well, we set a criteria so that any time it's measuring apatite, based on this criteria here, it will use these analytes to sum up to this value here. And in this case, because it's apatite, we do want it to use oxides. Unfortunately, we don't have a great data set to demonstrate this yet, but I will just quickly show how it's done. So you would click on this Edit Criteria button here, and you can have as many criteria as you like, and you can save criteria and load criteria in. So you can click on this plus button here to add a criteria, and we could put in a criteria called apatite, and we say we want to apply this criteria wherever P31 is greater than 1,000,000 counts. Now, this is actually using P31 underscore CPS because we're using counts per second, baseline subtracted channels, but the underscore CPS is actually inferred. So we can just use P31 in this case. And then we can right click here and tell it which elements we want to use. Now we could say select all, but we might want to leave out some of those lead isotopes because we don't want to measure those as well as lead. We don't include those as well as lead total. So we've set our iolites here, and now we're going to tell it what value we want it to sum to. And in this example, we're just going to say 96, and we're going to say, yes, we are expecting these to occur as oxides. And I'm just going to remove this criteria here. So then what this will do is anytime the phosphorus 31 signal goes above 1,000,000 counts, it will use this value and these channels and this constraint here. Like I said, we don't actually have a great example of this. You can try that out using this data set. It doesn't actually change the results that much in this case. But I do have some examples that have been provided by Danny Savard from UQAC, where he's been measuring samples that have sulfides in them, apatites, carbonates, magnetites, and tigerite, which I think is a high pressure form of serpentinite, and ilmenite. And in each of these, you may have things like sulfides, where we're not expecting them to be present as oxides. You have things like apatites and carbonates, where we're not measuring the volatiles, I'll say, for the apatites. And in carbonates, we're not measuring the carbon or the oxygen, so our sum value is actually quite low. Then we have things like magnetite, where we will be summing to 100%, and we do expect them to be in the form of oxides, but we're not expecting everything to be in the form of FeO. We're actually going to tell it that we expect it to be in the form of Fe3O4. So we can actually be really quite specific with these criteria for each of the parts of our sample. And the great thing about this is that when it runs, wherever the criteria match, iolite will record what it used. So you can actually plot up in the form of an image what criteria were used. There's a channel called criteria index, which goes from 0 to however many criteria you've set. In this case, Danny had set it up so that his first criteria was just called others, and you can see that they're just tiny little bits that are hard to account for, that are sort of quite often on grain boundaries. But the important ones that we look at in this example here are these apatites, which was criteria number 3. It's listed as number 2 here, but because it starts at 0. This was the third criteria, and these are in this sort of deep blue color. We have a big region of them here, and some big regions here, and big regions here. And we're going to also look at the calcite, which are these black regions here, in this case here. And the reason why they're an interesting example is because if we look at the raw calcium-44 image, what we can see is that it looks like our apatites, our phosphates, which are these big grains here, have about middle calcium counts. But our calcites, which are in this middle region here, which I think this is a vein of some sort, they actually appear to have quite high calcium counts. And that's really just due to yield factor differences. The calcite ablates much more easily than the phosphate, so it looks like it has higher count rates. But when we calculate our final calcium concentration image, we can see that they're actually quite the same, and that's what we'd expect using stoichiometry. One's about 55% calcium, the other one is about 56. So this is actually what the values should be. And it's a little bit hard to test this sum normalization approach because we don't have reference materials that have different criteria, different phases all mixed in with one another. But we can use this comparing our results that we get with stoichiometry to see how well our sum normalization works. And in this case, it seems to have worked really well. So we thank Danny for helping us out with that, and we'll be putting an example like this in our publication. One thing that I forgot to mention about using criteria is that we need to tell iolite for which selections we want to use criteria. So we can scroll down, and in this case we're only going to use it for our map, so we can just select all of our map selections. And then here in the elements, we're going to say, instead of using our list here, we're going to say use criteria. And that way it will know to use the criteria values instead of the values that we've set in this table. Now let's talk about affinities. As we mentioned before, this inter-element fractionation is related to differences in our sample matrices. And so when we're using multiple reference materials, it can be actually quite useful to work out which of those reference materials each of our samples most closely match. And by sample here, I actually mean selection. So within a selection, which reference material does it match most closely? We call this match between sample and standard its affinity, and it's based on its composition. We could set these manually. You can set these manually, where we just choose which reference material we think our selection most closely matches. Or we can get iolite to calculate which reference material is most closely matched to based on a nearest centroid classifier approach. And we can do that by using some set of elements to tell iolite what the composition is. And once we've done that, we can perform this downhole fractionation correction. Before we do that though, let's have a look at this spots experiment. So this was a spot experiment where we've measured some gabbro phases and we've measured some spots of NIS612, BCR2G, BHVO2G. And in this case, we're going to use BHVO2G and NIS612 as our calibrants and BCR2G as our test of this downhole fractionation correction. So let's open that experiment. I have it in my list of recent experiments. This is the gabbro spots. And what we're going to look at here, so if you open it, you can see that there's just a single laser log file and mass spec file. And again, you can see that we've measured some reference materials, and then we've measured our unknowns, and we have several blocks of those. If we go to the DRS settings and click on our DRS, you can see that I've already chosen some settings for us that we're going to be using BHVO2G and NIS612 as our reference materials, and we're using internal standards, and we're using calcium. But now we're going to work out this affinity for our secondary reference material, which is this BCR2G. And the way that we do that is that we select our reference material, so our selections, and we click on this affinity button up the top here. Now, as I said, we could just choose which one it's most likely to. And in this case, we only have two reference materials, BHVO2G and NIS612. And so we could just say, we know that BCR2G is probably more like BHVO2G than it is NIS612. So we could just set that. But what about our samples where we don't actually know necessarily what they're most like? Well, what we can do is we can say, use the majors to work out which reference material these selections are most like. So when I hit crunch, and I'm just going to uncheck these checkboxes up here just for this little experiment, just so we can show the effect. So now when we clicked crunch, it will do the same thing as it's done in the past, except that this is a much faster experiment. But now you can see that it's actually telling us that these selections have an affinity for, as in they are similar in composition to BHVO2G, and it's determined that using that nearest centroid classifier. So now we know for our unknowns, we're pretending this is an unknown at this point, that it is more close to BHVO2G. Why is that important? Well, if we have a look at some of our elements here and we click on this fractionation tab down here, it will show us the downhole fractionation relative to our internal standard. So remember, these are for spot analyses. So as we're drilling, as our time increases, we're actually drilling down into our pit. And so if you click on the different elements, you can see that there is actually quite a bit of difference between our elements. And for some elements, there's really not much difference. This is plus or minus, say, 5-10% for some of these elements. But if we look at something like silicon, we can see that there's quite a decent amount, and it's more than what we'd expect with noise. So for these ones, these could form a normal distribution, as in the within error of one another, but this one here for silicon, you can see that it's unlikely this is going to form a normal distribution by itself. So we want to perform some sort of downhole fractionation for this channel. Before we do that though, we're just going to have a look at what the results look like before we've done our downhole fractionation. So to do that, we're going to go to our time series tab, and we're going to plot up our silicon ppm channel. Now, because of some noise there, for our oxides, we're getting a lot of blowout in our range. So we're actually just going to click on the BCR2G group, and we're going to go to the first selection. And we're just going to click this visible button here so that we can see what it looks like. So can we see downhole fractionation here? Maybe. It starts a little low, gets a little bit high. If we click on the next one, maybe about the same. It can be a little bit hard with data like this, which is entirely normal data, to tell whether or not there is an evolution or a trend in this. So we've built a tool to make that a little bit easier. If you go to Tools and click Stacked Plot, it will actually plot up all of these selections for you at once. And this is exactly like the uranium lead DRS does for you in the DRS tab. And what it's doing here is it's plotting the start of each selection at 0 beam seconds for everything. And then it's plotting all of our selections, which are these colored data. And for each time point, it's calculating the average of all those selections. And that's this black line here. And what we can see is that when we do average out that noisy individual measurement data, we can see that there is a trend in our downhole. There is a trend with increasing depth or increasing beam seconds. One of the things we can use to estimate that is that at the moment we have an uncertainty of about 9,000 about this mean value. So now we're going to apply the downhole fractionation correction, and we're going to check our results again. Actually, just before we do that, we'll have a look at our uncertainty in another way as well. So if we go to the results view and we click on BCR2G and we click on output, and we're going to look at the silicon ppm channel, and if we hover over one of these, we can see that when we hover over them, the uncertainty is somewhere between about 3,000 and 4,000. This one here, we'll just look at this third one. It's about 4,000. It has an uncertainty of about 4,002 SE at this point. So now that we know that, let's have a look at what effect it has when we apply the fractionation correction. So we can click this button here to apply a fractionation correction. When we click it just once, it will automatically set the fractionation correction to be linear. And you can see in the fractionation tab, when we click this tab here, that it has applied a linear fit to these data. Now, why the affinity calculation was important is because we can see that the downhole fractionation effect is quite different for the two different reference materials. So we've got NIS 612 in purple, and we've got BHVO2G in this sort of greeny color, and you can see that they're quite different. So which one we apply will make a big difference to our final results. We can also click and hold on this fractionation button, and it will give us a third option for our fractionation fit. It was spline. And if we click that, you can see that instead of fitting a linear fit to it, it's now fitted a spline to it. So with that, we're going to click crunch data, and now when it's finished calculating the concentrations, it's going to apply a downhole fractionation correction for us. So just to see the effect of that, we'll go back to our time series view, and we'll click on silicon 29 again. We'll go to our first BCR2G run, and we'll click visible so we can see it. And what we can see now is that there doesn't appear to be any consistent trend with it. We can check that for all of our selections at once using the stacked plot. We can see here that there is still a little bit of a trend, which may be just residual stuff, but what it has done is it hasn't applied we haven't lost any time resolution by doing this, which is the important part. So I'm just going to double check that I'm checking the right channel again. And we can also go back and check this value. Just checking my results here. When we go back to our results here and look at our silicon value, we can see our uncertainty now is about 3,000 instead of 4,000. So because we got rid of that downhole trend, we've actually got rid of about a quarter of our uncertainty about this individual measurement. And it's about the same for each of them. That's because we got rid of that downhole trend. So it's actually a really big improvement to our precision for an individual measurement. So when I ran this the first time, I actually got a slightly different result, but you can see that you can correct these all the way down to being even more flat. And when we get that correction even further, it actually goes below 3,000, and so we actually can get an improvement on our uncertainty by up to about 30% just by using the difference between that and our original uncertainty. Now we're going to talk about the residuals correction, and this is the part that is a little bit hard to show, but it's also what we would call an experimental effect yet. We're going to include it in our publication, and we'll see how it goes in the peer review process, but it is completely optional. If you don't agree with it, you don't have to apply it, but we think it can actually squeeze out just a little bit extra accuracy for your results. So how does it work? Well, again, it works on this affinity process and any residuals that are left over from our corrections. So let's have a look in this example here. Actually, we'll just go back to the Gabbro's maps data set. Actually, it'll take longer to calculate, so we'll just stick with this one. So the idea is that if we go here and we open a secondary check, and we're going to show BCR2G, which is our unknown in this case, unknown in quotation marks, but we're also going to show our BHVO2G. Oops, sorry. We're going to show in this window BCR2G, and then I'm going to open another QAQC module by double clicking this over here, and we're going to look at, in this one, BHVO2G. Now what we can see is that in this, our results don't all come back at 0 because there is some residual uncertainty or offset for our calibrant. And knowing that there is a little bit of this offset, we can actually apply for that. So we can actually account for that. So if we go back to our DRS and we go down the bottom here, there's this experimental affinity correction. And if we check that and hit crunch data, what it will do is it will look at those residuals and it will actually apply those in our updated results. It's a little hard to show this, but I'm going to open a third QAQC module and I'm going to look at our updated values for BCR2G. So this is before the residuals correction, the affinity correction, and this is after, and you can see that it's actually improved our result. And I think if we was to look at our absolute value down the bottom, 73 there, and down the bottom here it's 42 or 43 say. So what has it done? Well, if we were to look at our first channel here, our first channel before the correction was about 4.5% off. And in our BHVO2G, our average value after all our other corrections has come out about 3% too high. So what the affinity correction does is it brings it down by 3%. So you can see we've gone from about 4.5% down to about 1.5%. And similarly with magnesium, it was about minus 3.8, but our residual on BHVO2G was low by about 1.78, so it's going to add 1.78, and you can see that it is now about minus 2 instead of being minus 3.8. So it's actually just applying these residuals to that we know haven't been accounted for in the rest of this process to our unknowns. And it works really well in this case because BCR2G and BHVO have quite strong affinities, they behave quite similarly, but it's important to remember this has been treated like an unknown in this whole case. We're not doing anything artificial to create that relationship. So you can try that out and see what you think about it, and let us know what you think about it. It's important to note, I almost forgot to say, that if the residual is greater than 15% plus or minus, then it won't apply that, because what it's saying here is that we're actually not getting a great result for nickel. Let's not make it even worse by applying some large residual. So if the residual is greater than 15%, then it won't apply that correction. So that's the residuals correction, and that's basically the summary of the DRS as it is at this point. I just wanted to mention that the code is open, so you can see all this. It's all been written in Python. It's about 2,000 lines or maybe even 3,000 lines of code, but it is all there, so you can see how it works and you can make changes if you want. It does come with iolite version for all versions after version 4.5. That was the reason why it ticked over to version 4.5, was because 3D Trace Elements was included at that point. We will be making changes to it and updating it from time to time as we make improvements to it. You don't need to do anything to include those changes, but you can also download it if you're interested in, say, forking it, making your own changes. You can download it from the GitHub page, which is available here. So with that said, I'd like to thank you for your attention and for attending the webinar. And if you have any questions, please let me know. Thank you very much.